Hello, my name is Dr. Benjamin Prather, and I'm here to try to present the Surreal Total Order. It's my second try. I tried last week, and my audio cut out 9 minutes in, so hopefully I don't have that type of issue today. Um, yeah, so a quick recap. I haven't done anything towards publishing that paper that I'm working on publishing, but I did actually look up a result on here. So there's a paper I need to read so that a few weeks down the road I can actually um, see if what I think I can actually show with these is actually one, still new, and two, possible to show. But first, I want to discuss what these numbers are, the surreal total order. And again, I discussed this sometime, but just as a review, if we let L and R be sets of numbers, where x of L is in L and x of R is in R, and no x of L is less than or equal to, no x of R is less than or equal to x of L, then x is this kind of set notation, except for we have this bar with the set L and set R in that order, then that is a number. And all numbers are made this way. I unpacked that definition a little bit last week, a little bit about like what we mean by set and how this means that they're layered by ordinals by birthday. And today, by the end of the day, hopefully we'll see that the motivation for this definition is the idea that we have the prior numbers and we're kind of doing Dedekind cuts. And so the left set is this L is the Dedekind set of the elements that are less than it, and this R is the ones that are larger than it. So X is kind of the number that's between the ones on the left and the ones on the right. So that's kind of the picture. These are on a number line. These are the ones to the left. These are the ones to the right. And X is a new number that we're introducing in between those. And but this definition includes this less than or equal to. So we need to define what it means for two numbers to be less than or equal to each other. And X is less than or equal to Y if there is no Y sub R less than X, and Y is not less than any X sub L. So for viewing this as Dedekind cuts, what we're saying is that we have X less than or equal to Y, and then Y, what we would expect Y to be less than or equal to any Y sub R, and X is less than or equal to any X sub L. So what we're saying is that this can't be less than or equal to that, and then this can't be less than or equal to that. So that's kind of what motivates those two things, is the idea that this is Dedekind cuts. But it turns out that this is something that we will need to prove. So we will actually prove that relation by the end of today, hopefully, by showing that that this actually defines a total order, and that X is in fact between those two, between anything in L and anything in R. Okay, but I think I may have talked about birthday zero, but it's worth repeating. So with birthday zero, then L and R must be subsets of the empty set, because when we start, we have no numbers. So our set of numbers is the empty set. Well, if your subsets, if they're subsets of the empty set, well, then that means that L equals R equals the empty set. And so the only possible number is this number where both L and R are empty sets. And just for symbolic notation, let's just give it a symbol that looks kind of like a slightly elongated zero, or circle rather. It's actually going to turn out to be the number zero. And just to double check that this condition is met, right? So the number, these have to be sets, but then we also have this condition that X sub L, that no X sub R is less than or equal to any X sub L. Well, this is vacuously true because there are no X sub R to be less than any X sub L. So if you list all these up, there is nothing to check. So this is vacuously true. So there we go. So we have immediately also that 0 is less than or equal to 0. And that is also checked pretty much exactly the same way. You just come up here, no Y sub R and no X sub L. Well, both of those are met because there are no x of r, and there are no x of l. So this is true and this is true. Also, again, vacuously, we have 0 is less than or equal to 0. So with birthday 0, we have our first number, and we can finally start moving on. So let's go to the next step. With birthday 1, we have L and R are a subset of the set containing 0. So that means that L and R are equal to the empty set or the set containing 0. So this is actually going to allow us to define 4 new symbols. We can now look at, well, we still have this one. We can have empty set, which we already defined to be equal to 0. In fact, I'll write that down here. And then we can put 0 on this side, or we can put 0 on this side, or in principle, we could have 0 on both sides. Okay. This one, it turns out, we're going to give the name 1. This one, we're going to give the name -1. And then this one over here, and for reasons, we'll justify the arithmetic notation for that in a future episode. But this one here, we note that since 0 is less than or equal to 0, we do in fact have that this XR is less than or equal to that XL. So that means that this is not a number. So we have to rule this one out. And so as we go farther and farther into birthdays, we end up pretty much, we can order all these. So this is a number that is less than 0. It actually, we could show that these numbers actually meet. I'll actually look at computations with these numbers when we have more arithmetic to deal with. So yeah, I just wanted to give an example of how the first few numbers are constructed, and then it gives you an idea for how things go on. But basically, they end up being Dedekind cuts of all the birthdays of all the numbers with birthday less than the one we're dealing with. Okay, so first I'm going to make some notes here of this definition. So this is pretty much notation that L and R are in that, and then X of L is an L, and X of R is an R. But it is useful to remember that by definition, we have that no X of R is less than or equal to X of L. And then from the definition here, it's useful to just make a note that X less than Y means that no Y sub R is less than or equal to X, and Y is less than or equal to no X of L. And conversely, X is not less than or equal to Y. It's just the logical negation of that. And the logical negation of this statement is some Y sub R is less than or equal to X, or Y is less than or equal to some X of L. Okay, so with that, we can start trying to look at some properties that are going to lead to being a total order. And the first one is the reflexive property. And for that, we're going to look at these 3 statements. So the first one that we're going to show is that, well, X of R is not less than X. And the second one we're going to show is that X is not less than any X of L. And then together, this will actually end up giving us the result that we want, that X is less than or equal to X, which is the property that's called reflexivity. Okay, and we're going to show all 3 of these. We're going to show that all 3 of these hold simultaneously by induction, by assuming that all 3 of these things hold for numbers with lower birthday and then show that they must hold for the numbers with the new birthday. So for the base case, these are all actually true because for 0, these are all vacuously true. Well, for 0, some y sub r or some x sub l, well, both of these are, for 0, there is none. So this is false and false. Sorry, if x, for this one, x sub r is not less than or equal to x. Well, for 0, there is no thing here, so it's going to be vacuously true because there is no x sub r. There is no x sub r here to deal with. And then for this one here, when you're dealing with 0, again, those are true because there are none to select. Okay, so assuming blah. Okay, let's go on to proving the steps. Okay, so if we follow this definition from here, what we're saying is that sum x sub r prime, this is some new thing in x sub r different from that one, is less than or equal to less than or equal to x sub r. Well, this is true because I could choose this to be the x sub r to be in fact that, and then by 3, this is true. Or, I don't care about the other condition because with an or statement, as long as that one is true, we're good. And similarly for 2, some condition, this one here, some, it actually looks like some right element of the x sub l we chose is less than or equal to x. Well, I don't know if that's true or not. That's a little bit hard to determine. But I have this or statement, and the or statement that I need to check is that x sub l is less than or equal to some x sub l prime. Well, I'm assuming that the x sub l exists, because even in here it implies that the x sub l exists. So if x sub l exists, then x sub l must be less than that, because I could pick the exact same one that I picked up here, and then so that is true by 3. Just pick the one we had to start. And that works for both of them. All right, so now that we have these two statements, and these two statements are proved by assuming that this one is true at the inductive step. And now for 3, well, what this statement is saying, I just replace x for both of these. No x sub r is less than x, and x is less than or equal to no x sub l. But if we look at this one, no x sub r is less than x means that if I pick any x sub r, that's the same thing as that x sub r is not less than that. So that's really just another way to say 1, and that's just another way to say 2. And so since 1 and 2 have already are assumed true by the inductive step, that now shows that this statement is now true. So if we have this true in the base case, this is all true. And then when we actually examine the base case, the beauty of this definition and having the birthday 0, the base case, we go all the way down to birthday 0, and these statements become vacuously true in that step. Okay. So that has covered reflexivity. So we now know that the surreal numbers are reflexive. So the next thing that we need to look at is the transitive property. And this one, if you were able to lip sync, if you were able to read my lips last week after my mic went out, which is a little bit difficult because I'm facing the board a lot. It's hard to read lips when they're facing the board and you can't see them. But I actually had a hole in this part of the proof yesterday that I said I was going to have to, last week, that I said I was going to have to fill in this week anyways. But let's look at transitive. Transitivity. So for transitivity, what we need to have is that if x is less than or equal to y, and y is less than or equal to z, then x must also be less than or equal to z. Okay, so we're actually going to prove this one by a common proof technique. We're going to assume the negation and then show that that leads to a contradiction. So the negation of an if-then statement is we're going to assume that all these things are true. But then we have to negate that one. And x is not less than or equal to z. All right. Well, what this means is that, well, from this condition, no y sub r is less than or equal to x, and y is less than or equal to no x sub l, and no z sub r is less than or equal to y, and no, and z is less than or equal to no y sub l, and sum z sub r is less than or equal to x, or z is less than or equal to sum x sub l. So now we have two cases. So for this red case here, well, if that case is true, well, we also have x is less than y, and we have that no z sub r is less than y. But by induction on z, we know that that now is, we're assuming that this statement is false because we're trying to prove this statement, so this statement is false. We're trying to show this statement is false. So for case one, the red case is false because we have z sub r is less than or equal to x, x is less than or equal to y, and z sub r is not less than or equal to y. Similarly, for this green case, we have z is less than sum x sub l. We have y is less than z, but then we also have that z is less than or equal to no y sub l. So then we have y is less than or equal to z, z is less than or equal to sum x sub l. But then we also have that y is less than or equal to no x sub l. So either way, we get to the evaluation of this statement here. I'm going to note that this proof is actually interesting because if we assume that this statement is true, then we have this true statement here, and in both cases it's actually true. So no matter what, it's true. But if we assume that it's false, then we have this or this, and in both cases they're false. So it shows that it's false. So basically, whatever we assume at this state, we've actually shown that it's going to be whatever that is. So this is actually the case. This is actually an example of why, with an induction proof, you actually need to go back to the base cases.